Hello, welcome back. Let's do another LeetCode problem today. Today we will talk about unique paths in a grid. This is number 62. We are given a grid. We know that there's a robot that initially located in the top left corner of this grid, and it tries to move to the bottom right corner. The robot can either move down or right. We're given the dimension of the grid. Our job is to figure out how many unique paths the robot can take to reach the bottom right corner on the top left corner. So let's take a look at some examples of a path. For example, this will be one path from start to finish. This one is another path, another unique path from start to finish. And here's a third unique path. The question asks, how many unique paths are there in total? There are many approaches to this problem, but today we're going to do a dynamic programming approach. Here, I make a DP matrix, which we're going to store all the states. The DP matrix would have the same dimension as the grid provided from the input. Our job is to populate this matrix, and we will establish all the unique paths to every cells in the grid. And then finally, we're going to return the value at the finished cell. So that will tell us how many unique paths are there from start to finish. Now let's try something very simple. Let's populate the first cell on the top left. How many unique paths does it take to get to the start position? Well, there's only one. We just stand there and that's our position. Now let's talk about the cells on the top row. For example, for this cell, how many unique paths does it take to get to that cell? Again, it will be one because we can just move from left to right. How about this cell? It's also one because the only way you can get to that cell is from the cells on the left. So essentially, it's the same path. For each cell, we are just extending this path by one cell. So we can say that the value for the top row is all ones. Building from the same reasoning, let's take a look at this cell. How many unique paths does it take to get to that cell? So it's only one because we can only go down from there. And this cell is also one. Again, it's the same path and we are just extending this path by one cell each time going downwards. So the column on the left, all the values are 1. Okay, so now let's talk about the remaining of the cells. So let's go with this one. How many paths does it take to get to that cell? There is this way and this way. So 2 unique paths to get to that cell. Now, how about this cell? How many unique paths there are there? Well, we can go this way, and this way. So 3. So the value is 3 in this cell. The pattern is that because for any cell in this portion of the grid, the number of unique paths for that particular cell is the sum of the unique path from the cell above and the number of unique paths from the cells on the left. This is very intuitive because the robot can either move downwards or it can move to the right. So for any given cell, the previous position, the robot is either came from the cell immediately above or immediate to the left. After the robot lands on the current cell, the path just extends to all the paths from the cells above and all the paths of the cells immediate on the left. So it's a sum of these 2 directions. So now that we understand how to populate this matrix, let's jump into the code and actually do it. This C# code is provided in the GitHub links below. We are given M and N, which are the dimension of the grid. M is number of rows and N is number of columns. So first, I initiate a DP matrix with the same dimension as the grid. And then I will use a for loop to populate the top row of value to be 1. Similarly, I will use another for loop to populate the value of the first column as 1. Now, I use a double for loop to loop through all the remaining cells of this DP matrix. Notice I start with the cell 1, 1. So that's why the index starts at 1 here and 1 here. So as we recall from the last slide, for every cell in this portion of the matrix, the value of that cell is the sum of the value of the cells above and the value of the cells on the left. So that's what this line is. And at the end, when this is done, we just return the value for the cells in the lower right. So it's very, very easy. I just want to talk about the runtime complexity because we're iterating every cell of the grid. The runtime complexity is the size of the grid, or m times n. Okay, let's take a look if this works. And it looks good. This question is relatively simple. In the next video, we will do a similar question in which obstacles are introduced in some cells of the matrix. And again, we will determine number of possible unique paths the robot can take going from the upper left to the lower right cell of the grid. Okay, hope to see you in the next video.